Good morning. Hi. Hello. Today we start with chapter 6. Chapter 6 is about a new way of analyzing the performance of algorithms, specifically the performance of online algorithms. And online algorithms are assessed, their performance is analyzed with what is called competitive analysis. And we're going to motivate online algorithms with a ski rental problem. And then we're going to analyze a very simple algorithm, online algorithm for the ski rental problem, the so-called break-even algorithm. We're going to prove that it is too competitive, that is at most 2 times worse than an omniscient offline algorithm. And then we were going to prove that this is actually optimal. No online algorithm can do better than too competitive. And we're considering another important and ubiquitous online problem, namely the paging problem for memory cache. We're going to rigorously analyze the least recently used strategy that you're probably aware of, that is very commonly used as a heuristic. But in this course, we're going to perform a rigorous analysis. We're going to prove that this is K competitive, where K denotes the number of cache pages available. Then we're going to similarly analyze the least frequently used strategy, and we're going to prove that this is not at all competitive. It can behave arbitrarily worse than the optimal omniscient offline algorithm. We're going to prove that least recently used online algorithm is actually optimal. So no deterministic online algorithm can do better than being K competitive, but we're going to show that randomization can beat this bound, specifically for the ski rental problem. We've proved before, we will prove that too competitive is optimal for deterministic ski rental. But at the end of this chapter, we will prove that a randomized algorithm can solve the ski rental problem and be 1.6 competitive, which is better. So that in the end of this chapter, we're kind of going to combine the two chapters 5 and 6. We're going to combine a randomized analysis with a competitive analysis of online algorithms. So that's our plan for this and probably the next session. So to start, let's consider the motivation, the ski rental problem. What is ski rental about? Let us use this opportunity to recall the different kind of algorithms and the different kind of analysis we've seen so far. So the classical algorithm, kind of algorithm that you're all aware of since maybe CS300, there's some data to be input to the algorithm. Then the algorithm processes that data, and finally, upon termination, it produces the output. But that simple principle, input, processing, output, does not cover all applications. There are many applications where this simple paradigm simply does not apply. And but the general analysis that you're all familiar with since CS300 is this is a deterministic algorithm. Analysis refers to the worst case possible input, let's say of a given length, and that's a classical analysis. We've already seen variations of this classical analysis, namely randomized algorithm. That's an algorithm that during the processing phase can flip coins, can make internal decisions based on randomness. So here the coin flip is part of the processing of the algorithm. And this kind of randomized algorithm are analyzed in expected case, right? So this is how, for instance, the quicksort, randomized quicksort was analyzed with analyzed primality testing, Miller-Rabin. We have analyzed polynomial identity testing. This is what you're currently implementing. And we've analyzed the test where the given graph has a perfect matching. In this sense, so the input in all these cases is some fixed data that is read. And once the reading of the data is finished, then the processing starts, and the processing involves some randomization, some coin flips. On the other hand, there's also average case of analysis. So what's the difference? In average case analysis, we use deterministic algorithms. So here the processing does not flip any coins. It's a entirely deterministic process. However, the input data arises from some random process. It's a kind of, we suppose that the input data is produced randomly according to some certain distribution. Okay, so so here the coin flips pertain to the input data. We suppose that the input data is produced randomly, and then we analyze the performance of the algorithm on such a random or a typical input, deterministic algorithm, and finally it produces the output. An even more different paradigm is where the input data is not finite, but is a continuous sequence of input. This is not covered by all the previous paradigms. All the previous paradigms here suppose that the input is given, is read, and then the processing starts. Whereas when the input keeps coming, then the reading of the input can never stop, and the processing must keep going on. Such algorithms are, for instance, important when analyzing networks, router, for instance, right? So a router cannot read the input data and then start processing, but while processing, more data keeps arriving, and the router better keeps on computing and never stops. But while it keeps computing, it must already start producing output. So this is sometimes called stream algorithms. So these kind of algorithms should not stop, right? Imagine a router stopping operation, right? That would be terrible, right? So these kind of algorithms, both input and output, continue to be coming, and the processing keeps going on. And we're going to, in this chapter 6, we're going to consider a special kind of such stream algorithms, namely online algorithms. And this is what I'd like to introduce now, motivated with a ski rental problem. So suppose you're on vacation and you're, right, it's winter, there's snow, and you're given the choice whether to rent a ski for 1 day. So let's say renting a pair of skis costs $1 per day. And or you could buy a pair of skis. Let's say this costs $10. Don't bother too much about the actual absolute values. This is, of course, much too cheap for real. But this is to demonstrate, to motivate online algorithms. So once you have bought a pair of skis, then you don't need to rent anymore, right? On the other hand, buying a pair of skis is a considerable investment that may or may not turn out to pay off, right? So if you want to go skiing for only 4 days, then definitely renting will be more beneficial. That will only cost $4, whereas buying will cost $10. On the other hand, if you're planning to go skiing for 15 days, then it's better to buy right on the very first day, spend the $10, because renting for 15 days would cost $15, which is more. And so the problem you're faced with is the choice whether to buy once or whether to rent repeatedly. And this, of course, depends on how how many days you're planning to go skiing, or more precisely, it also depends on how long the skiing season will last. So imagine, for instance, on the first day, weather is fine, there's lots of snow, and you go skiing, and maybe you rent because you're cautious character. So maybe first time skiing, better rent $1. Now the next day, it's also great skiing weather, and maybe now you start considering to buy. So um, so maybe you rent for another day, second day, so I've spent $2 renting. On the third day, it's still great weather. Now you decide you like skiing, you make the investment of purchasing a pair of skiers, so that by now you have spent a total of $12, 2 days for rent, and on the third day, make a purchase, so that for all future days you don't need to spend money on renting anymore, because now you own a pair of skis. But unfortunately, well, fourth day still goes fine. So you enjoy your newly purchased pair of skis on the fourth day. So you still have spent a total of $12. But on the fifth day, it turns out that the weather becomes warm, or the snow melts away, the skiing season is over, and now you're stuck with this investment of $12, right? $10 for the ski, $2 for 2 days of rent, where in the end you only could use your ski for a total of 4 days. So in retrospective, it would have been better to rent for these 4 days rather to spend a total of $12, or even uh, to spend once $10 on the first day, but only retrospectively. This is, of course, even easy to say looking back what would have been the best decision. Um, and yeah, so, but when you present it with the option when starting the skiing seasons, it's impossible to predict. Um, so this is the essence of a online problem. You cannot see the entire input in advance. You cannot know in advance how long the skiing season it takes. Uh, the weather news comes in day by day, first day, second day, third day, fourth day. So every morning, new weather is revealed by looking out of the window, and every morning you're faced with a decision whether to keep renting or whether to switch to purchase once and for all. So that's the essence of an online algorithm. The input is presented one by one, day by day, but still you have to make a decision without knowing the future input. That's an online algorithm. And how do we analyze the performance of an online algorithm? Well, it's easy. It's always possible to fool an online algorithm, right? So we can, for instance, uh, any online algorithm. Let's suppose an online algorithm for the ski rental problem keeps renting for a few days and then um, decides to make a purchase, and then we uh, in analyzing the performance of the algorithm, we decide or we create a worst case for this algorithm by now switching to to thawing weather that where all snow is gone, right? That's the worst case for the online algorithm, right? So it's not reasonable to compare the online algorithm to absolutely, but instead what we do in online algorithm, we perform a competitive analysis. We compare the online algorithm for an arbitrary but fixed input sequence. We compare that to an optimal omniscient offline algorithm. So that means we take our online algorithm and analyze it for a certain sequence of inputs, and we consider another algorithm that knows this very same sequence of inputs in advance. That's why it's called omniscient or offline. And then we compare uh, which algorithm performs better and how much better. Well, of course, the omniscient algorithm will never perform worse than the online algorithm, but how much better will the offline algorithm perform? This is called the competitive ratio, and this is a measure of how good the online algorithm performs. So let's apply this measure of analysis and of performance for online algorithms to the ski rental problem. Um, So to recall, ski rental, the input is the weather, and the weather is presented day by day, morning by morning, and the algorithm has to make a decision whether to keep renting or whether to switch to make a purchase once and for all. And this decision has to be made every morning without knowing the future of the weather, without knowing the entire input. The entire input would be the entire sequence of weather informations, but this is not available to the online algorithm, only to the offline algorithm. So the decision to be made by the online algorithm on every morning is whether to rent for another day, in this example at a cost of $1 per day, or whether to switch to buying once and for all. And in the previous example, purchase was $10. More generally, let's consider the case that buying a pair of skis costs $D, where D is a natural number that will determine the performance. So that's we're looking at an entire family of ski rental problems, one for every possible choice of D, one for every possible choice of how much a pair of skis will cost. It is no loss of generality to suppose that renting costs $1 because in the end what really matters is only the ratio. How much more expensive is buying than renting? Of course, if buying costs only $1, then it's always the best choice to always buy on the first day, right? Because if renting and buying is at the same cost, then that's an easy choice. So the interesting case is when buying is strictly more expensive than renting, and of course, the more expensive buying is compared to, it is relative to renting, that will affect what the optimal online algorithm will look like. Okay, so, and we'll compare the performance of an online algorithm with an optimal omniscient offline algorithm. An offline algorithm is defined to be one that somehow miraculously knows the entire input sequence in advance, that knows or is given the entire weather information for the entire season day by day, and therefore is able to make the best possible choice. So for the ski rental problem, as an offline problem, what is the best possible choice? Well, it depends on how long the season is, how many days of skiing is possible. So let's call this number the length of the season. That's denoted by L. So the offline algorithm uh, is told or knows in advance that the season will last for precisely L days, where L is a natural number. And then depending on which one is larger, D or L, it's better to rent or to buy, right? So more specifically, if the season lasts for less than D days, then renting is cheaper. Then renting costs a total of L dollars, right? L days at $1 each. That means it incurs a cost of L dollars. So if D is larger than L, then renting repeatedly will be the best choice. And this, by definition, is the choice made by the optimal offline algorithm. Whereas if L is larger than D, then it's more beneficial to make a purchase on the very first day, right? And the offline algorithm can make that decision because it, by the definition, it's omniscient. It knows how long the season will last. And if both are equal, right? So if the length of the sequence L is equal to the cost D of renting, of purchasing, then it makes no difference, right? Whether we rent for D days or whether we buy once at the cost of D, that's in the end, that's the same. So to summarize, this is the optimal omniscient offline algorithm. Check how long the season will last. If the season lasts for less than D days, then rent for L days. If the length L of the season is larger than D, then buy on the very first day. So that the cost incurred by the optimal offline algorithm is the minimum of the two, right? So if L is smaller, then the total cost of this algorithm is L dollars. Whereas if D is smaller, then the total cost incurred by this algorithm is D dollars. Does it make sense so far? So this is the optimal offline algorithm against which we will compare the performance of an online algorithm. More precisely, the online algorithm we're considering is called the break-even algorithm. So what is break-even? Break-even algorithm proceeds as follows. The break-even algorithm is an online algorithm, so it does not know in advance how long the season will last. It must make a decision every morning after looking out of the window and seeing the weather. So the renting algorithm the break-even algorithm performs as follows. It will rent for D minus 1 days, provided that the season lasts that long. So every morning it will keep looking out of the window, and if it's less than D days have passed and the season is still going on, then it will keep renting for another day, until having reached D minus 1 days. And if the season is still going on the next morning, the D's day, then it will switch to make a purchase. So that's why it's called break even, because on the D's day, it would have spent D dollars purchasing, and that's the same amount as it costs to actually making a purchase. So once the money spent on renting starts to break even with the investment of purchasing once and for all, then the break-even algorithm switches to making a purchase. That seems like a reasonable algorithm online because it makes a decision every morning uh, by only knowing the current weather, not able to predict how many days the season will last. So then what is the cost incurred by this break-even algorithm? Well, again, of course, it will depend on how long the actual season is, only that the break-even algorithm does not know this. Namely, we claim that the cost of this online algorithm is the minimum of L and 2D minus 1. So let's understand why this is the case. So suppose that the season lasts for less than D days. If the season lasts for less than D days, then the break-even algorithm will never reach the D minus 1 days for renting. It will every morning it will look out of the window, see that the season is still going on, and will rent for another day. And after L days, the season is over. So it will not have reached D minus 1 days, because we're considering this case where the minimum is attained by L, so that the total money spent by the break-even algorithm in this case, when the season is shorter than D days, will be exactly the length of the season L. However, if the season lasts longer than D days, at least D days, then the money spent by the break-even algorithm is first D minus $1 for the first D minus 1 days where it rents every single day. And then on the Dth day, recall that the algorithm on the Dth day, if the season is still going on, will switch to making a purchase once and for all. And that purchase costs another D dollar, so that overall the break-even algorithm will have spent D minus $1 for renting and another D dollars for the purchase. And that's a total of 2 times D minus $1. Whenever the season lasts longer than D days, that's the amount spent by the break-even algorithm, right? So that now we have two algorithms, an online algorithm, the break-even algorithm, which we have currently analyzed. Break-even algorithm does not know the value of L, the length of a season, but we have been able to analyze its cost depending on whether the length of the season is shorter than D or longer than D. In the first case, the cost is L. In the second case, the cost is 2D minus 1. And we have the optimal omniscient offline algorithm that knows the length of the season L and therefore can make the right decision from the very first day. And its cost is the minimum of L and D. So in online algorithms are analyzed in competitive analysis, and competitive analysis compares the performance, compares the cost incurred by the online algorithm under consideration to the cost incurred by an optimal omniscient offline algorithm. So this quantitative is called the competitive ratio. So this is the cost of the online algorithm currently considering divided by the cost of the optimal omniscient offline algorithm. And of course, for this analysis to be able to perform this analysis, it is necessary to know an optimal offline algorithm. But in this case, with the ski rental problem, that was easy. Which decision is to be made by the optimal algorithm. So what we want to do now is we want to compare these two quantities, the ratio between the two. And again, this will be subject to correction later. So let's now, just for training purposes, apply this and prove that the ratio incurred by the break-even algorithm divided by the cost incurred by the optimal offline algorithm is at most 2 minus 1 over D. So in particular, it's less or equal to 2. That means that the offline break-even algorithm may in general perform worse than the omniscient algorithm, but never more than 2 times worse. Actually, strictly less than 2, because there's this minus 1 over D, where D, recall, denotes the cost of purchasing, and this cost is of course known to the online algorithm though. What the online algorithm does not know is the length L of the season. Okay, so I'm going to postpone the proof of this inequality. This is a purely mathematical analysis statement. I will give this in the next session. And so to summarize, the break-even algorithm is 2 minus 1 over d competitive. That's the gist. That's what I'd like you to remember about the break-even algorithm, the same way that you remember that bubble sort is quadratic time, quicksort is n log n, binomial heap is log n time for every single operation. So break-even algorithm is 2 minus 1 over d competitive. That's how we analyze online algorithms. And following our virtues of computer science, the next question is always to ask whether this is optimal. Remember, that's what we also asked about quicksort, whether n log n is optimal. And we used decision trees to prove that indeed any comparison-based sorting algorithm requires at least n log n. So quicksort or heap sort is indeed optimal. And similarly, the question here arising here is whether there's a better online algorithm that is better than the break-even algorithm, an online algorithm that achieves a better, a smaller competitive ratio that comes closer to the performance of the optimal omniscient offline algorithm. And we're going to show, this is the rest of this slide, we're going to show that this is not the case. We're going to show that the break-even algorithm is indeed optimal. We're going to show that any online algorithm will have a competitive ratio that is at least 2 minus 1 over d. And this is attained by the break-even algorithm, so this is optimal. So what we're going to show and to consider is we're going to consider any possible online algorithm, and let's call this A. And we're going to show that this arbitrary and unknown online algorithm will not be better than 2 minus 1 over d competitive. And as usual in proving an algorithm optimal, this is a very difficult problem, right? Because we need to argue about any possible algorithm. And when we have argued about sorting algorithms, we have achieved that by considering decision tree based sorting algorithms, right? So that was our important key insight, that we could consider decision trees and prove something about decision trees, and that would then apply to all possible sorting algorithms, even those that nobody might have found so far. And the same approach we will do here. We'll consider an arbitrary but unknown online algorithm, call it A, and we're going to, in a thought experiment, we're going to run that algorithm on a season which seems to go on forever. So we can do that in our analysis. We can just suppose that the season is very, very long, and I'm not going to tell you how long, because we're going to kind of execute the algorithm. Every morning the algorithm gets up, look out of the window, and we tell the algorithm it's still snowing. Next morning algorithm looks out of the window and we tell it's still snowing, and we're going to record which decision this algorithm A, which is arbitrary and unknown, which decision this algorithm will make. And eventually this algorithm will switch to buying, right? So initially maybe, or maybe not, it will rent, but eventually at some day, at some morning, the algorithm will switch to buying. Otherwise, the algorithm will incur unbounded cost, right? So if the algorithm keeps renting forever, as long as the season lasts, then the cost will be L. And that's, of course, much worse than the break-even algorithm, whose cost will never exceed 2 times d minus 1, right? So Eventually, this algorithm will switch to making a purchase, and we're going to analyze the cost it thus incurs in dependence on the number of days the algorithm has rented. Let's call this number X, so that the total cost incurred by this algorithm will be X plus D, right? And of course, we don't know X, but certainly X exists. So the algorithm is supposed to rent for X days, and on the X plus first day, it will make the purchase. And now what we in our analysis do in our thought experiment is we will run the same algorithm again, but this time we will run the algorithm on a series of weather data that makes the season last for X plus 1 days. So that on the morning of the X plus first day, just right when the algorithm, on the morning of the X plus second day, the season will be over. So that since this is a deterministic algorithm, what will algorithm do in this weather data? It will again keep renting for X days because initially it is presented with the same weather data as our initial thought experiment execution or thought run where the season would last indefinitely. So the weather to the algorithm, the weather seems to be the same, but once the algorithm now in this execution switches to making a purchase on the X plus first day, then on the X plus second day, we shut down the season. So that in this case, the algorithm will have spent a total amount of, well, X days for renting and X dollars for renting and D dollars for the purchase, and then the season is over. So in the thus created weather scenario, we have created a worst case weather scenario, a worst case input sequence of weather data, and we've analyzed what this arbitrary hypothetical online algorithm incurs on this particular worst case sequence of weather data. And according to the paradigm of online algorithm, we're going to compare that and determine the ratio of this algorithm's online cost to the cost incurred by an omniscient optimal offline algorithm. So the optimal offline algorithm in this case knows that the season will last for X plus 1 days, will be shut down on the X plus second day. So that's a difference. The online algorithm does not know. The online algorithm looks out of the window every morning, and we, in our analysis, we can kind of create a worst case weather data sequence, whereas the offline algorithm knows whatever weather sequence we're going to present to it in advance. So the offline algorithm will simply check which one is cheaper. Is it cheaper since the season lasts for X plus 1 days? Is it cheaper to rent for X plus 1 days, incurring a cost of X plus 1? Or is it cheaper to make a purchase, which costs only D dollars? So that the offline algorithm, which knows both quantities, X and D, will make a decision on the very first day, depending on which one is smaller, and therefore incur the total cost, the minimum of the two quantities. So that now, in our competitive analysis, we have to compare these two quantities. We have to determine the ratio. So this is the ratio, online cost divided by offline cost. That's a competitive ratio. And we determine this competitive ratio for this arbitrary, that's important, for this arbitrary online algorithm for the ski rental problem. And this ratio is X plus D divided by the minimum of X plus 1 and D. And the claim is that this ratio will be always greater or equal to 2 to the 2 minus 1 over d, or put differently, the worst case weather sequence we have just in our analysis created, even in this worst case, or in this worst case, an arbitrary online algorithm cannot perform better than the break-even algorithm, cannot get lower in competitive ratio than 2 minus 1 over d. And this proves that the break-even algorithm is optimal. So it's the best competitive ratio that can be achieved comparing the online algorithm with offline algorithms. Of course, the offline algorithm will in general do even better, right? But that's easy to achieve because it's omniscient. Okay, so that kind of concludes our first example, analysis, design and analysis of online algorithms. We've designed the break-even algorithm, a very simple algorithm. We have analyzed that. We've determined its absolute online cost depending on the unknown quantity L, the length of the season, which the algorithm does not know. And we've compared its performance to an optimal omniscient offline algorithm, which does know the length L of the season. And we've seen that the ratio that our online algorithm will never perform worse than 2 minus 1 over d times the offline algorithm. And that means, in our new terminology, that this online algorithm break-even algorithm is 2 minus 1 over d competitive. And then we have proven that this is optimal. Any online algorithm will be at least 2 minus 1 over d competitive. So that's the best possible competitive ratio that can be achieved for the ski rental problem when it comes to deterministic algorithm. And a key tool in proving the optimality was kind of an adversary. We, in our analysis, we've tried to make the arbitrary and general online algorithm A perform as bad as possible. Namely, we have first run the algorithm on an indefinite season, and then we have observed its behavior, and then we have run the same algorithm again on a season that changes the weather just right after the algorithm decides to purchase. So we have kind of made an adversary, a worst case sequence of weather data, and this is called an adversary argument in online algorithms. Okay, so, and then we have analyzed the optimal offline algorithm on modified sequence season. We've analyzed both algorithms on a modified season that is modified such that it looks the same, that it depends on X number of days that the online algorithm chose to rent initially. Good. So then let's move on to another popular online problem, namely paging in caches. So let's recall the characteristics of online algorithm. The input is revealed only gradually to the online algorithm. It cannot first read the entire input, then process, and then output, but it has to start making decisions based on partial knowledge. And we analyze such online algorithms' performance, its output, its cost incurred in comparison to an hypothetical, omniscient, optimal offline algorithm. And the ratio between both costs, that's what we call the competitive ratio. And the famous online problem is the paging problem. So what is paging about? As you recall, computers have this memory hierarchy. The fastest memory are the processor registers. They're really I mean, we're talking about less than 1 nanosecond to access such a register. On the other hand, there are very few such registers, maybe a total of 100 bytes. Next level is the level 1 or level 2 cache on or next to the processor, which is a little bit larger, some megabytes nowadays, but the access is slower, like 2 nanoseconds. Next level is the dynamic random access memory, which is maybe 4 gigabytes. So it's again much larger, but also noticeably slower in terms of maybe 15 nanoseconds access time. And even larger are the hard disks. Nowadays it's SSDs. It used to be magnetic hard disk. These are size of terabytes, and access time again becomes significantly slower. We're talking about 10 milliseconds because it involves some movements. And even larger and even slower are maybe tapes. So in order to speed up computation, an algorithm usually doesn't know where its data is currently resides, and it's a job of the computer hardware and of the operating system to try to put the data that the algorithm currently uses on top levels of the hierarchy so that the algorithm can access it quickly. But of course, the operating system and the hardware cannot know in advance which data the algorithm uses. Experience tells that algorithms are usually local. So when they have used a certain memory cell, a certain data item, then it will probably use it again sooner or later. So that gives rise to some strategies for maintaining a cache. So let's consider the following situation. We have only two types of memory for simplicity. We have fast memory, but that's small. Only K pages, only K items can be stored in the fast memory. And we have a slow but large memory, which can store capital K pages, capital K memory items. And so imagine in this picture that we have these two kinds of memory: magnetic disk, very large but slow, and dynamic RAM, smaller but faster. And the size of the disk is denoted by capital K, and the size of the random access memory is denoted by small k. And the dynamic RAM contains some pages, some items. In this case, for instance, we have 6 pages, and the content of each page is not the actual data, but the content here, for instance, the number 19 is supposed to indicate it, that the memory stored here is the content of the 19th cell of the hard disk. So it's not the number 19, but it means here we are caching the content of the 19th block of the hard disk. Here we're caching the 5th block of the hard disk. Here we're caching the 8th block. Here we're caching the 2nd block, 11th, and so on. Okay, and so this is how the fast memory is used in order to cache, in order to accelerate access to the large but slow magnetic disk. And now comes the algorithm that starts to access the memory, the magnetic disk, and the algorithm is not supposed to know that there's a cache in between. So everything should be transparent to the algorithm. And when the algorithm tries to access the 8th page number 8, now this page is already present in the cache in the fast memory. So the algorithm can reach this data very quickly. Everything is good. It can read, it can write. And next, let's say that the algorithm um, accesses page memory number 1. This is not in the cache, right? Page number 1 is not present in the cache. It is here on the hard disk. So what will our operating system do in this case? It will try to move that page from the slow hard disk into the fast cache, but the fast cache is already fully occupied, right? So the operating system has to decide which of these 6 pages in the cache to evict, to store, to move back to the hard disk, which means writing. For instance, the operating system may choose to evict page number 11 here. That means write the possibly modified contents of page number 11 back to the hard disk. And now this page in the cache has become free, has become available. And now the operating system can load the page number 1 from the hard disk into this now free location in the cache, and then can continue executing the algorithm, which can now access this page number 1 fast from the cache. And so on until the algorithm wants to access another page. Maybe in the next, the algorithm wants to access page number 8 again, which is good because this is already present in the cache, but maybe in the next step, the algorithm wants to access page number 11. And then we're in trouble. Then the operating system is in trouble because it has just evicted page number 11, right? So page number 11 used to be present in the cache, available for easy access. But when the algorithm wanted to access page number 1, the operating system, let's say, has decided to evict page number 11 to make room for page number 1. But now in the next round, the algorithm wants to access page number 11, so that now the operating system has to evict another page to recover page number 11. And of course, in retrospective, it would have been more beneficial for the operating system to keep the page number 11 here and instead evict some other page that the algorithm may not use for a longer time. But that's the essence of an online problem. The operating system does not know in advance which page the algorithm will access the next time, right? So if the operating system knows that right after accessing page number 1, the algorithm will access page number 11, then the operating system will maintain page 11 in the cache and instead evict another page, preferably the page that the algorithm will not use for the longest time in the future. Maybe page number 5 will not be used in a long time, maybe never again. Maybe it's already done using that page. Then this should be evicted. But the operating system does not know this. Maybe in the next step, the algorithm does use page 5 and will never use page 11 again. So that means for the operating system, the paging problem is to decide when the algorithm accesses a new page, which other page in the cache to evict, which page the algorithm hopefully will not use for a long time. And this is an online problem because the operating system only gets to know one by one which page the algorithm will access next. So the algorithm here in this example, let's say the operating system has decided to evict page number 5. So it stores page number 5 onto the hard disk, thus making room for in this page of the cache, and then loading page number 1 into the cache. And maybe in the next round, the algorithm will access page number 11, which is good, it's present, or maybe the algorithm will now try to access page number 5, which is bad. So, and the operating system does not know, so that this is a typical online problem. And let's formalize this problem. So we're going to consider a sequence of accesses. So let's say the length of the sequence is n. The algorithm runs for a total number of n rounds, making one access in each round, accessing one page on the hard disk, numbered between 1 and k, capital K. And we want to analyze or to find an algorithm that performs well, cache maintenance strategy for an algorithm that only gets to know the sequence one by one, gets to see the sequence, input sequence one by one. And the goal is to minimize the number of cache misses, because every cache miss initiates an eviction, storing choosing one page in the cache to be evicted, store this page onto the hard disk, and instead load the newly accessed page into the cache. That's called a cache miss. And popular strategies for paging are least recently used, least frequently used. So least recently used evicts the page in the cache that has not been used in the longest time, least recently, whereas least frequently used evicts the page in the cache that has not been used for the least number of times, that has not been accessed for least frequently. Other strategies, for instance, first in, first out. So that's kind of the opposite of least frequently used. Or minimum, just evict the page with the least number. So when the algorithm wants to access page number, a new page, then in this case, currently page number 1 is the one with the least number, and this will be evicted. These are 4 examples of online algorithms for the online paging problem. And we want to analyze these rigorously, thus making these algorithms actually algorithms. Otherwise, they are heuristics. And what we're going to do next is we're going to analyze least recently used. So we're going to perform a competitive analysis of least recently used strategy. And to this end, we consider an arbitrary but fixed sequence of accesses of the algorithm, a sequence of length n. And remember, least recently used is the following online algorithm. Whenever a new page is accessed that is currently not present in the cache, this gives rise to a page fault, cache fault. Then the page gets evicted from the cache that has been least recently used. Okay, LRU strategy. So here we have such a possible arbitrary sequence of accesses, and this symbol is used to indicate that a certain page here, the page is not given a number but a symbol. This page is being accessed, but it's not in the cache, so this means page fault occurs here. And we want to prove that LRU has competitive ratio k, where remember small k denotes the number of caches. Or particularly want to prove that LRU, in general, of course, it may be worse than the omniscient optimal offline algorithm, but it will never be worse than a factor of k, where k denotes the number of pages in the cache. Put differently, the larger the cache, the worse LRU seems to perform, but the worse it performs in comparison to the omniscient algorithm. And of course, that can never be reached. So in the special case where we only have one cache cell, right, then there's nothing for LRU to choose from, right? So when we have only one page of cache and the algorithm wants to access a new page, then it's clear which page we have to evict, because there's only one page. And in this case, LRU performs exactly the same way that an optimal offline algorithm performs, namely it is one competitive. But when there are two pages in the available of cache, then LRU will perform at least twice as bad, or at most twice as bad, and so on. So that's a statement. That's what we're going to prove. But this proof, yeah, time is almost over. We postpone this proof to the next session. That's wrap things up for today. Thanks for your attention. So we'll resume on the next session with a corrected analysis of the online break-even algorithm, and with a proof that least recently used paging strategy is K competitive. Thank you and see you.